The following lecture is recorded and produced by Momin Ahmed Rizvi, and the accompanying note for this lecture can be found on AurParho.live, and it is called Polar Coordinates, Further Pure Maths 1. So if you have that downloaded, open it up now, or if you don't have it downloaded, go ahead and download it and open it up now because it'll be useful to follow along with that note during this lecture.
Okay, let's start with polar coordinates again. So we talked about what polar coordinates are, how to convert from polar to Cartesian and Cartesian to polar of not just one point but also of graphs. If you have been given r equals something, how do you get into Cartesian from with y equals something, right? And the next thing that comes up would be, first of all, sketching of polar graphs, right? If you've been given r equals to something, how do you sketch it? And this is the first, this is the first thing that comes up next. The second thing that comes up next is the calculus part of polar coordinates, right? Both the derivatives, the slopes, and the integrals, the areas. Right. So let's look at sketching first. Let's look at sketching. Right. So in your CAIEs, as far as sketching goes, you need to know certain basic graphs. For example, what does a plus b sine theta looks like for any a and b? What does a plus b cos theta looks like for any a and b? What does cos a theta looks like? What does sine theta looks like? What does r to the e to the theta looks like? What does r equal theta? And once you know these basic structures, you can do most of the sketching part for any A and B's. But for example, if you come across something like r equals e theta cos theta, and you don't know what it looks like because you haven't come across the basic structure for this. So what you would do is you would take certain values. For example, take pi over 6, take pi over 4, take pi over 3, pi over 2, and so on. And you would get certain values of r, right? And then you would try to sketch the graph to the best of your ability. You do not need to sketch it perfectly. You just need to show the examiner what the general shape looks like. So maybe your pi over 6 comes up somewhere over here. Maybe pi over 4 comes up somewhere over here. Maybe pi over 6 comes somewhere over here. And then you connect all those dots. Maybe you get something like this, right? And one more thing, since we're on the topic of sketching, I would like to talk about the concept of negative distance from the pole, or negative r. And don't quote me on this negative distance, because distance is never really negative. So, but this is really more of a conceptual thing. So if you one thing I should mention here before this is that when you're practicing how to sketch different graphs, or you come across different graphs that you don't know the value of, I would recommend you use certain graphing softwares such as Desmos and GeoGebra, right? And what these softwares do is basically you give them the function, and these tell you what the graph looks like, what the graph exactly looks like actually. And a lot of the times when you're sketching, you need to confirm your answer, and the marking scheme really doesn't show the graph, right? So these two are very good, not only to verify but also to increase your understanding of the graph. So, for example, if you're playing around with Desmos, you might understand what roles certain numbers play. For example, this is a very basic example, but example nonetheless. If let's say you come across the linear equation mx plus c, and you plug in values into Desmos, you might realize that increasing the values of m has the effect of making it even more steeper, right? If your m is very close to 0, your line is very close to being parallel to the y-axis, right? You might play around in Desmos and figure this out, and this is just a basic example. This goes for a lot of these graphs, right? You might play around with the values of a and try to understand how it changes the graph, and it really helps when you're sketching a general graph in your mind when you're solving these questions, right? So let's come back to the concept of negative distance. So let's say if you and me are both at the pole again, right? And we need to go at a park X, right? I could tell you that, okay, face 225 degrees and then walk 3 units, right? Let's say I don't want to say that for some reason. I just don't want to say it. What I could also say is face 45 degrees, right? Just face 45 degrees. So you're actually facing this way, and then walk 5 steps backwards instead, and you would reach at the same point, right? So what negative r really means that you travel along the same distance in the line, either y equals x or y equals negative x. For example, if I say face 120 degrees, right? So this is 120 degrees, and then walk 5 units backwards, you would actually walk this way, right? So you are facing this way, but since you're walking backwards, you're going this way. Right, so that's the concept of negative R. And actually, Cambridge does not expect you to know this. Cambridge doesn't want you to know this. But in my opinion, it is better if you know this, because a lot of the times when you're sketching and when you maybe get answers, you might wonder why a certain why certain graphs aren't there, or why certain answers seem extra. This is probably the answer. So for example, the graph of sine theta, right? The graph of r equals sine theta is a perfect circle. Oops, please recognize my poorly drawn circle. Thank you. From 0 to 2 pi, right? And you might wonder, well, okay, there's something here, but why isn't there anything from in this quadrant and in this quadrant? And the answer actually is that in the third and fourth quadrant, sine is negative, right? So what really happens when sine is negative? Let's zoom in on this. Okay, so let's take our 45 degrees, right? Sine of 45, the value of r is, actually I can write over here too. The value of r is 1 over root 2, right? This is 45 degrees. And if I take 45 degrees from here, the value you're facing this way, but the value of r is actually 1 over root 2, so you travel on the same distance over here, right? So whatever was in this quadrant went to this quadrant, and whatever was in this quadrant went to this quadrant. Hence, from 0 to 2 pi, the graph is actually a perfect circle that looks something like this, right? And that's all there is to sketching. You would want to practice a bit more so that you get a hang of it, and we practice a bit more. Uh, and just remember, you don't need to plot it exactly, just the general graph, right? So let's come to the next part, that is the bigger part of polar coordinates, and maybe a bit more annoying part because of all the algebra, the derivatives and the integrals. Excuse me. Okay, so let's say, okay, which example should I take? Hmm. Okay, let's just take an example from the notes. For example, if you have r equals e theta cos theta, right? It might look something like this. I don't really know right now. It will probably look something like this maybe. But anyways, uh, For example, if you're given this, right? If you're given this and they ask you what is the maximum or minimum distance from the pole, or just r, right? So they're asking you maximum or minimum values of r, and if you're coming from calculus you probably have a hint where you're going with this, right? So let's say this certain graph, let's say at this value of theta, this is hard to draw. You'll have to imagine mostly. At this value of theta, this is the r. At when you increase theta, r is also increasing, r is again increasing until maybe this point. After this point, r starts to decrease. So they're asking you what is the value of theta at which r is at a maximum distance from the pole, right? So what you do is you take d theta equals 0, right? And just a recap what d theta is. D theta is basically small change in r over small change in x. So we're figuring out how much r changes as theta changes for very small values, and if we set it equal to 0, for example, over here the change in r is positive as theta is increasing, right? As you increase theta, there's some more value of r there is, right? And so oops for up to this value of theta, the d theta was positive because after each theta there was some increase in theta. So maybe from till theta, maybe the graph looks something like this, right? And after this point, the radius starts decreasing. So the radius at this point is bigger than the radius at this point, right? So after this theta, this starts decreasing. So all we need to know is what is the value of the turning point over here. What is the value when it's at its peak, right? So we would take dr d theta. So what is the derivative of e theta cos theta? Let's use our chain rule. This is u, this is v. Let's take uv prime plus vu prime, the product rule, sorry. So that would be e theta cos theta, right? And derivative of cos theta is negative sign. So negative e theta sine theta, and let's set it equal to 0. Let's take e to the theta common. Cos theta minus sine theta equals 0. This is 0 when either of these are 0. So e theta equals 0, or cos theta minus sine theta equals 0. Cos to the theta is never 0. Cos theta equals sine theta. Tan theta equals 1. And you get the values of theta as pi over 4 and 5 pi over 4. Right? 5 pi over 4, and then again at 5 pi over 4. So these are the values of theta, and these are your answer. And what it means is that at some pi over 4, the values of r were increasing until you reach the theta as pi over 4, and after that the values of r started decreasing, right? And this is your dr d theta. And the next bit more interesting part in my opinion is more of dy d theta and dx d theta. So let's say I have I'm going to need to draw a bit clearer graph for this. Let's say I have this graph. Okay, let's say I have this graph. So first of all, at any point, right, if I take at this point, there's some value theta, and there's some r value. At any point, the y component is y equals r sine theta, and at any point, the x component is r multiplied by cos theta. And we already talked about this. Just to show you quickly, this would be theta, this would be r. So sine of theta, this is y, this is x. Sine of theta is r over y, so r is y sine theta, right? And cos theta is, oops, this would be y over r. Hmm, y is equal to r sine theta. and cos theta would be x over r cos theta would be x, right? So these are your two components. So if you have any graph, right, if you have any values of r and theta, you could find the horizontal component by r cos theta, and you could find the vertical component by r sine theta. Whatever r is, you just multiply it by sine or cos to find the vertical or horizontal component, right? So first of all, let's take a look at the derivative. So at any point, how do you find the slope of this graph? For example, at this point, it might be something like this. At this point, this might be something like this. At this point, there's something like this. Right. So for any, if you're given r equals to a function of theta for anything, you can first of all find y component in the sense that multiply it by sine. So sine theta this, and then x component would be cos theta multiplied by r. Right. So this is how you get the y component. This is how you get the x component. And we know that gradient is the change in y over change in x. So for any point on the for any point on the curve, right, you can get its slope by taking dy over dx. Dy over dx basically means how much y changes as x changes for very small values. So it's what the gradient looks like on a single point, or how it would look like as the change in x and change in y are very, very small as they approach zero, right? So first of all, what I would like to clear over here is this is actually dy over d theta, and this is actually dx over d theta, but the theta cancels. It's dy over d theta because this is y in terms of theta and this is x in terms of theta. And when we put this in a fraction, the d theta and d theta cancels, right? So for example, I have this curve, right? I have this curve r equals a times 1 plus sine theta. And this would look something like this. This would look something like this is a, this is 2a, this is a, this is 2a, 2a, 2a. Right? The curve looks something, the curve, let me draw with a different color. The curve looks something like this. This is what the graph looks like. And let's say I ask you, at what value of theta is the tangent to the curve perpendicular? Actually, let's take the parallel case. But at what value of theta is the tangent to the curve parallel to the initial line? This is the initial line. And at what value is its gradient parallel to the initial line, right? So for any line that is parallel to the x-axis, we know that its gradient is zero. You know its gradient is zero because there is no change in x. There is no change in x as there is no change in y as x changes. Hence, dy over dx is zero, right? So if I'm asking you at what value is the tangent to the curve parallel to the initial line, all I'm asking you is when is dx d theta equals when is dy d theta equals zero, right? When is dy d theta equals 0? And we know that dy over d theta dx over d theta, when dy over d theta is 0, of course the whole fraction is 0, and hence this is a horizontal line which would be parallel to the initial line, right? And the other way you could think about this is that, for example, at this theta, the y component is this, and then as you increase theta, the y component is increasing until you reach this line. When you reach this line, this is at its peak. This is the highest it gets, and then after this, if you increase theta, it starts to decrease, right? Then it starts to decrease. So all we're asking, what is this value of theta at which it's at its peak? And from the graph, you can probably tell that it would be pi over 2, but this is an easy graph. That's why you can tell. What about those you can't tell about, right? So what's the way to do this?